Imagine that you have the graph of a function z equals to fxy. So here's the x, here's the y, and the going up is the z-axis. And the graph is going to be some surface. And let's say there's some point here which is the maximum. You can also think of the minimum. These max or min are called extrema. And just like in the single variable calculus case, if you're trying to solve an optimization question, often the question involves figuring out the local max, local min by using derivatives. Okay, so we're trying to do the same thing over here. And one thing that you can think of is like, if you're at the top of the mountain, question, if you are at the max point, what would gradient of f equal to? And that's an interesting question because we know by intuition that gradient is a vector that points to the fastest increasing direction, right? But if you're already at the top, where do you go? Nowhere, right? So what do you think the gradient would be? Zero. Zero. Okay. So the answer is it's zero. Okay. Yeah. Another way to think about it is like if you're at the top, then whether you look at the partial with respect to the x direction or partial with respect to the y direction, see, partial derivatives constitute the gradient, right? These two together, if you form a vector, that's the gradient, right? But partial derivative means you're trying to take the cross-section with respect to the x-axis and you're looking at its rate of change in the x direction. And the x direction would be simply zero, right? Yeah, because it's at the highest peak, the derivative is zero, right? And that's true for both x and y, so you end up with both components of the gradient being zero, so that's what you have. So appropriately, such a point is called a critical point. So definition, if gradient of f at a comma b is equal to zero, we say a comma b is a critical point. Now recall that in one variable calculus we used to call such a point as critical number. And we say it's critical number because it's a single number, right? But here you have a pair of numbers that would make the gradient equal to zero, so now it's a point in the two-dimensional plane, so we call that a critical point. So number, point, that's like a slight change in the terminology there, but the idea is the same. In one variable calculus, we used to say if the gradient is actually or D and E, just for technicality. If the derivative is zero or does not exist, we call that point that number x value as a critical number, and same it's the same deal. Okay. Now we're not going to go over the pathological case when the derivative does not exist. It's just too much. We'll just limit our cases to only when the functions are differentiable. So you don't have to really think about that. We'll just consider this as the critical point. Okay. Now, in the one variable case, not all critical points or not all critical numbers were relative minimum or maximum. And you know that because there are some cases when you have something like this, right? In one variable case, you might have a point where you do have a horizontal tangent line so that the derivative is zero, so it's a critical number. However, it's neither relative minimum or relative maximum, right? So it was still possible to have such a thing. In the three-dimensional case, in the multivariable case, when the graph is three-dimensional, now you have some more complicated cases. Here's an example of a critical point which is neither a relative max or relative min. Yeah, so say. So this point right here. Oh, another way to think about this is like, what's the tangent plane at the highest point? Will be a flat horizontal plane, right? Yeah. So same deal. If you have gradient equal to zero, its tangent plane would now become the horizontal one. But here you do have a point where if you think about the tangent plane, it is the horizontal one. So if you only think about this cross section, definitely you have a straight line giving you a tangent line, right? And if you only think about this other direction right here, you do have a tangent line like that, and those two tangent lines can span an entire plane, right? If you can think of a plane that contains those two tangent lines, and that will be considered as a tangent plane to this surface at that point. It's a bit weird because that plane is going to cut through this surface, so that may make you a little nervous, but it is indeed a tangent plane. And that point is neither a relative maximum or relative minimum, because if you follow the red, that point is the maximum, but if you follow the blue, that point is the minimum, right? So such a point is called a saddle point. So remember, we were talking about this surface, two-dimensional surface, as a saddle. Yeah. So that's going to be another problem that we have to face. Okay. All right. So because of this, we need a criteria for figuring out if there is any saddle point. And here's how you do it. So, criteria for finding if a critical point is a relative max, relative min, or a saddle point. And this is similar to the second derivative test that we were doing in Calc 1. Do you remember the second derivative test? So what was the second derivative test for a single variable function? So let's say you had f prime of c equal to 0, so that c is a critical point, okay? Critical number. And then if you had f double prime of c to be positive, then at c, what do you have? Relative max or relative min? Yeah. Yeah, it has relative min, because if the second derivative is positive, you have the happy clown, right? And at the bottom, you have the minimum, right? Yeah. On the other hand, if you have f prime of c equals 0, so it's a critical number, but f double prime of c is less than 0, then what do you have? You have the sad clown. And the second derivative negative, you draw the sad clown, and then you have the relative maximum. So that's what was known as the second derivative test. And there's this like in between where f double prime of c equals to 0. In that case, we don't know what would happen. It could be this one or that one, or it could be neither. It might be something like this as well. So we never know what happens. So the second derivative test has a blind spot. It doesn't tell us. It doesn't always give us a result. Sometimes it will say this test is not good for this function. Now here, we also have such a blind spot, but again, going through those cases in multivariable becomes too complicated. So we will not deal with the cases where all of the second derivatives are 0. That's just too much. Okay. So here's the criteria. It's somewhat similar to this one. So I'll leave this here. So what you do is first we say being a critical point, we know that the gradient of f is 0. So let's say gradient of f at a comma b is 0. Let's say that. Okay. And then over there we define the Hessian of f, which is like this. You do f xx, f xy, f yx, f yy. So the Hessian is, we're taking the second derivative just like the second derivative test, but the catch here is that in two variable case, you have two variables you can differentiate with. So you can differentiate by x twice, or then you can differentiate by x and then y, or you can differentiate by y and then x, or you can differentiate by y twice, right? So that's what you have. Okay, and this here means it's a group. It's the what is it? Determinant. So if you have a determinant, how do you calculate? It's AD minus BC, right? So that's same as fxx, fyy minus fxy times fyx. But it turns out that the partial derivatives commute, whether you differentiate by x first and then y, or whether you differentiate by y first and then x, it's the same thing. You get the same end result, so we're just going to say this way. So that's the Hessian. Okay. And then you have three cases. Case 1, if fxx is positive, so it's like this one, right? And Hessian of f is positive, then a comma b let's write it like this. Then f has a relative, what is it, max or min? Min. Oh, it's smart. I'm recording, come on. I have to put my time to delete that part. It's not good. All right. Okay. Okay, so as you can see, if the second derivative is positive, it's the smiley face. So gives you a relative minimum. Okay. Case two, if fxx is negative and h of f is positive as well, then f has a what? Relative max. Now, imagine the following. What if that matrix fxx, fxy, fyx, fyy. Let's just assume that this part is zero, so it's really easy to think about. If you have 1 here and then negative 1 here, what does that mean? That means in the x direction, it's a smiley face, right? But in the y direction, what do you have? You have a frowning face. So if that happens, what kind of shape do you have? You have a saddle, right? If it's smiley on one direction and frowning on the other direction, that point in the center would be a saddle point, right? So, and as you can see, what's the determinant here if you took the determinant? 1 times negative 1 minus 0 gives you negative 1, right? So that's exactly what happens in case 3. If h of f is less than 0, then no question asked. If this happens, then the f has a saddle, okay, at this point a comma b, right? So that's what it is.
I have a question.
Yes.
Where did you get the determinant from? Like, how do we?
Yeah. So that's a fair question. Why are we talking about determinant all of a sudden? Well, to really do justice to what that's saying, let's say u hat is, say, n comma n. So yeah, I could also use cosine comma sine, but then everyone gets scared. So let's just say m comma n. So u hat means it's a unit vector, so m squared plus n squared is 1. So it's some unit vector, okay? Now, what we really want to say is that if it's a local max, then its second derivative in any direction should always be negative, right? Then it's local max, right? Or if it's a local minimum, then its second derivative in every direction should be positive, right? So if you were to do du hat of f and then do another du hat, so you take the two directional derivatives of this function at a comma b, well, first of all, this by definition is f differentiated by x, and you multiply by n, plus f differentiated by y multiplied by n. Because all I'm saying is, like, what is this? That's the formula for directional derivative is you have the gradient of f dotted with u hat, right? So because gradient is just you differentiate by x, differentiate by y, make it a vector, and you're doing the dot product with mn, this is what you get as the first derivative, right? But then you have to do this again, du hat, and then you have to plug in xy as ab later. Then what you have to do is you have to take this and differentiate by x, so fxx times n plus fxy times n times m plus, and then you have to differentiate this by y. Sorry, this should really be yx. Yeah, well, that doesn't, like, I'm distinguishing, but they're the same thing, so it's not important. Fxy, and then m fyyn times n. That's the second derivative, and then you have to evaluate it at a comma b. So what is that? That's like fxx m squared plus, this is the same, but let me distinguish that. Fyx nm plus xy mn plus fyy n squared. Okay, so that's the directional derivative, right? And then a nice way to repackage this is by using this this matrix form, which is you put fxx, fxy, or should it be yx? Now it might be yx, but it's okay, yeah, because they are the same. Fyy, and then you put mn here, mn here. You should verify that these two are the same, because first of all, if you do this times that, you get fxx times m plus fyx times n, okay, as the first one. And then if you do this times that, you get fxy times m and fyy times n. So you end up with a row vector that's size 2. And then when you calculate that with this one, you end up with exactly this one. Now the question is, what is this? Well, this is why you need to take linear algebra next semester, okay? Because if you learn linear algebra, you learn that this is what's known as a bilinear form, because it takes two vectors and produces an output. And there's something called eigenvalues and eigenvectors, and especially because these two are the same, this is what's known as a symmetric matrix. So if you have a symmetric matrix, then you always have two eigenvectors that are orthogonal to each other, okay? And that's, you have like two directions where you have the maximum value of the concavity and minimum value of the concavity, right? And there's something else that you learn in linear algebra which says that the determinant is the same as the product of the two eigenvalues. And if you have one direction which is smiley, which means that value is positive, because that's the second derivative. If there's a perpendicular direction which is negative, then you end up with this value being, you end up with this value being negative. Okay? So depending on m and n, you're just scanning 360 degrees and trying to find all the second derivatives. And this is a formula. And it says the maximum value of this is the highest eigenvalue of this matrix. The minimum value of this thing, as you scan 360 degrees, that is the minimum value of this eigenvalue. And the product of those two values is same as the determinant of this thing. If that's positive, that means both eigenvalues are positive or both eigenvalues are negative. So this condition here, what this is saying is that the eigenvalues, if it's positive at one point, one direction, it stays positive everywhere. This is saying if the eigenvalue is, what this is saying is that if the second directional derivative is positive in one direction, then it's positive everywhere. Or if it's negative at one point, then one direction, then it's negative everywhere. That's because the maximum second derivative and the minimum second derivative multiplied together is positive. So either they're both positive or both negative. Yeah. So that's the deep reason why you end up with this. It has to do with the linear algebra. So in other words, linear algebra is really powerful. If knowing linear algebra will allow you to just write this and it's just obvious thing. Yeah. If you don't know linear algebra, I mean, I tried my best to where it rises from, but it gives you some motivation to run more linear algebra. Okay. Okay. So in this class, we will just accept that this is what it is, and of course, when the Hessian is zero, then you have a problem. None of this applies, and that's the blind spot to this, but we will not go there. Okay, all of our examples will be a case where Hessian is either positive or negative at the critical number. Okay. All right. So let's do two examples to see how this thing works. Okay. So every critical point will be also called singular point because it's somewhat different. And no, that's not right. Determine the nature of extrema. That's the right. Okay, so all right. So you have this second. So you have this two variable function, and you're trying to find the critical points and see if it's relative max, relative min, or it's neither. It's a saddle point. Let's try to figure that out. Solution. Well, critical points are places where the gradient is zero. What's a gradient? Well, you just write down all possible first derivatives and make it a vector. That's what a gradient is. So you differentiate this by x. If you differentiate this by x, this becomes 2x. If you differentiate x by x, you get 1. So it's 1y. Y squared is considered as a constant because we're doing a partial derivative, so that just gives you 0. 3x differentiates to 3. Okay, in the same way, if I differentiate by y, this time x squared is considered as a constant, so it's 0. If you differentiate by y, that's going to be negative x plus 2y. And 3x is also considered as a constant if you do the partial derivative with respect to y. So that's all you get. And therefore, you get 2x minus y plus 3, negative x plus 2y. Okay, now you can say 2x minus y plus 3 equals to 0. And you can say negative x plus 2y is equal to 0. And both of these derivatives must be 0 in order to be called a critical number. Therefore, now you have a system of equations. How do you solve a system? Well, you can always solve for one of them and then plug it into the other. So I can solve it for x. See, if I move the x to the other side, you see that x is equal to 2y. And that gets plugged into the first one so that you get 2 times 2y minus y plus 3 is equal to 0. So that 4y minus y gives you 3y. Move the 3 to the other side, you get negative 3, which yields y is negative 1. And if y is negative 1, you can plug it into this formula. You get x equals to 2 times negative 1, which is negative 2. Okay, so we figured out our critical point. The point is negative 2 comma 1. Now, negative 2 comma negative 1. Now you calculate the Hessian. What is the Hessian? Well, it's the determinant of all possible second derivatives, right? So we already have this as f differentiated by x, and this is already differentiated by y, so let's just differentiate this one, okay? So what is fxx? Let's see. So what is fxx? Well, that means you're differentiating fx by another x, and oh, by the way, I'm using subscripts for derivatives because it's easier to write that way. Hopefully that's not going to confuse you. So this is already f differentiated by x once, right? So we take 2x minus y plus 3 and differentiate it again by x. What does that give us? Just 2, right? That's it. The other ones are constant, so if you differentiate by x, it's 2. Okay. How about fxy? Well, that's like fx and differentiating by y, which means I'm taking the same thing and differentiating by y. What does that give you? Negative 1, yes. Okay, let's try fyx. Fyx is fy differentiated by x. Fy is negative x plus 2y. We're trying to differentiate this by x. What do you get? If you differentiate this by x, you get negative 1. And as you can see, they are the same. Yeah. In fact, this will always happen. There's some condition like second derivative needs to be continuous or something. But for we will limit the cases when we don't have to think about that. So in most cases, the second derivative is whether you differentiate by x first and then y, or y first and then x, you should be getting the same thing. Okay? In fact, you can use that as like a test to make sure that you're not doing something strange. Okay? If you're doing correct calculations, these two should always be correct, equal. Okay? Fyy would be taking fy and differentiating another times by y. So what do you get? You get 2. Somehow these two are the same too, but that's just coincidence. In many cases, they're not the same. Okay? Usually they're not the same. Okay, so therefore, what we are doing is we have 2, negative 1, negative 1, 2. And if you do AD minus BC, we get 4 minus 1, which is 3. And the important thing is this is positive. Okay. All right, so what do we see? We see that fxx is positive, right? And then Hessian is positive. Again, the intuitive meaning of the Hessian being positive means that we already know that if this is x and that's y and that's z, the function, if you do a second derivative in the x direction, it's positive, right? Which means it's a smiley face there, okay? But then if the Hessian is positive, then regardless of the direction, if you go 360 degrees, any direction that you go, the second partial will always be positive. That's what the Hessian being positive guarantees. Okay? Since it's a smiley face 360 degrees, that means that point is, this point that we just found, negative 2, negative 1 is a minimum, okay, relative minimum. Okay, so therefore, since fxx is positive and h of f is positive as well at negative 2, negative 1, which is the critical point. It's a critical point because we know that at these two places, both of these are 0. So gradient 0, okay? We see that fxy has a relative minimum at negative 2, negative